Everybody knows Faruk. He's going to talk about what you see on the slide. Specifically, I think there are multiple things. So I don't want to wait much longer because he will also do a real life demo of his new viewer for LayNii IDA, it's called. And yeah, please, Faruk.
Thank you, Renzo, for the invitation. So let's get started. First, a quick disclaimer. I am working as a researcher and software engineer at Brainovation, and I am affiliated with the Maastricht University. So I developed analysis tools, mostly in LayNii, and I do YouTube videos to disseminate my knowledge and expertise. And currently, I am working on imaging and analysis of 0.35 millimeter MRI data in living humans. So my talk will have two parts. The part one, meso veins, this will be more anatomical, and part two will be fMRI. And there I will have more interactive part of the talk. And hopefully you will be able to see like how these two parts interact with each other, because like what I've been investing my time on with regards to imaging the anatomy of the veins and arteries in the living humans kind of translated into fMRI, and some things I like found there, then translated back and so forth. So hopefully this will become clearer to you. So first, just to start from some basis, there are some constituents of the cortex. Often in neuroscience, we talk about cytoarchitecture and myeloarchitecture, but there's another very important constituent, that is the angioarchitecture of the cortex. And it is even more important for us, the, let's say, fMRI people or the people who study the living human brain. So most of you might be familiar with the seminal paper of Duvernoy, the French scientist, I believe, neuroanatomist, and he was particularly famous for his angioarchitectonic staining method, which created the following textbook rendering. This is actually a hand-drawn illustration that many of you might be familiar with, that depicts a human brain with the veins in black and arteries in color. So well, we have that image in our mind's eye, and now let's connect it closely and quickly with the fMRI. On the left-hand side, you can see the data. Actually, this is the default test data set that we share together with LayNii, that is recorded by Renzo in Leipzig, I believe. This is the motor cortex, finger tapping, and you can clearly see that there is this black thing in the middle that is almost pulsating together with the task activity. And usually I ask, when do you think it is the activity, or when do people think, when do people finger tap, whether this part is dark or white? But now I will just answer. Well, I mean, actually funny, like when I ask this, people say, oh, people are finger tapping when this guy is black. Whereas it's totally the other way around, because when it is black, this is a large vein and it is highly deoxygenated. Together with the finger tapping, the oxygenated blood rushes in from the arteries and floods the veins, and it becomes less dark, as explained by Hogenrath in 98 and also even Ogawa in 1990, by looking at the difference between oxygenated and deoxygenated blood and how it affects the T2 star weighted signal. You can see that in the rest, the vein has a dark surrounding, and the activity, it becomes more similar to the gray matter. So just all this to say that, like, when you are doing fMRI, you need to care about the veins. That's to me like a given and not even needs to be questioned. Whereas, like, finally, when I give such talks around, like, people often say, oh, but why should we care about the veins? Like, I want to see the neurons, right? Well, you do, but you do fMRI, so you need to know about the veins first. So now I will quickly transfer to layer fMRI connection. And this drawing is inspired by Bob Turner's 2002 paper called How Much Cortex Can a Vein Drain? I kind of read that paper and extended the argument in that paper towards the laminar level or the mesoscopic level, let's say. So the story goes more or less like this, at least in my mind. You have some piece of the cortex. This is gray matter cube. There are neurons in it, and there is some neuronal activity. This neuronal activity, of course, means that it needs to be supplied with oxygen and other nutrients and so forth. So there is a vascular system to support these neurons. And here is drawn the capillary network in simple bars that are connected to an ascending vein, let's say, that becomes a pile vein that's connected to other pieces of the cortex, and then eventually they connect to large, big veins. And basically the story is the following. So you might have some percent signal change there in the capillaries, and if the whole area is active, it is kind of accumulated. this extra oxygenated blood in this ascending vein. So you should see a bit higher percent signal change if you just look at the voxel inside this vein. And maybe if there's a big area, you might even see like a higher percent signal change in the pile veins because they are pooling like all the area together and giving us stronger oxygenated versus deoxygenated comparison signal. But of course, like it doesn't always go high. Like it doesn't mean that the more you look at a larger vein, the more percent signal change you will see. No, because when you go to really large veins that are basically draining from all the other areas of the brain that are maybe not active, your signal now becomes diluted and percent signal change goes down. I mean, this is the story given by Bob Turner, basically. Now I just put it into the context of the layer fMRI and like looking inside the gray matter, cortical gray matter. And obviously I didn't draw here, but there is all this artery part of it. This was like a simpler story about the veins. So now I would like to study all these like veins and stuff. And now I would like to briefly give you the status quo in vascular imaging. Actually, you can find that at least looking at studies that publish data from below 0.5 millimeter in at least 2 image dimensions, that's my definition of mesoscopic, you can see some early studies like Koopmans 2008, and then there are a few other studies that are at 0.35 millimeter isotropic level. And although I mentioned this because Saskia is my collaborator and she does really like a time of flight imaging at very high resolution, but this is mostly arterial parts. So whereas the other parts of these images are mostly like vein dominated images. When I was looking at the literature, I noticed that, well, most of the recent, let's say, mesoscopic T2 star weighted imaging has rather early echo times and very long acquisition times. Like you see like 42 minutes, right? And of course, if you have an anatomical image that takes 42 minutes to acquire for the whole brain, this comes with lots of challenges, such as you need to account for the head motion. You need to use the prospective motion correction system and so forth. So this becomes really like a hassle to figure out. In Saskia's data, she had 12 minutes per slab, but she had many slabs to cover the whole brain. So this still adds up to maybe more than an hour acquisition time. However, when I was looking at the Peter Koopman's paper from 2008, I have realized that there is an opening for further optimization for particularly venous imaging at 70. And that opening is drawn on the right-hand side here. You like just ignore the squares and just have a look at the smooth curves here. And basically it shows that up until 40 milliseconds, maybe a little bit lower than 40 milliseconds, 70 really has like a better contrast for venous tissues compared to the non-venous tissues in the human brain, compared to 3T, and obviously at 1.5T. So which means that we can extend our readout duration up until 40 milliseconds and not like try to stay so low, like 10 milliseconds and so forth. And basically use this as a way of getting like a more data. Luckily, I was not the first person thinking about it. And I remember actually discussing this with Renzo, even when he was in Maastricht around 2022. And luckily, in the meanwhile, Rüdiger Sternberg from Bonn University came up with a new acquisition, a new implementation of 3D EPI. And he showed example images that are, for instance, at 0.4 millimeter isotropic resolution and whole brain T2 star weighted images. And very nice acquisition times. This is just taking 6 minutes. However, when I looked at his data, I noticed that he's again like pushing for earlier echo times. Here it is like 19 milliseconds. So together with Dimo, what we basically did, looking at all these openings to optimize our protocols and what other people are doing and so forth, we decided to do multi-shot, multi-echo 3D EPI. So rather than single echo, we wanted to have this multi-echo aspect to it for like several reasons, and use the 3D EPI implementation by Rüdiger Sternberg. And nicely, actually, pretty quickly, we have converged on a very good acquisition protocol that gives 0.35 millimeter isotropic images for the whole brain with 3 echo times separately, and the acquisition time is just below 7 minutes. So this is now really like talking about 40 minutes to acquire T2 star weighted data to like we came down to like basically 7 minutes, right? And 7 minutes, you can really live without, I believe, I mean, maybe not in the clinical context, but you can really live without too much worrying about the head motion during the scan. You can instruct your participants well, and you can make them comfortable, and it just works. So now we went ahead and collected such data at 70 in Maastricht. And the other constraint that we wanted to have was that we wanted to make everything work at the scanner. So we could have been way more fancier with regards to our acceleration or reconstruction strategies, but we wanted to create something that people are ready to use, so it doesn't require offline reconstruction. And I say this because actually we can make this protocol way faster, but then the reconstruction fails. Like if it takes, let's say, a couple of minutes to acquire the data, but it takes 5 to 6 minutes to reconstruct the data. If you stack a couple of them in the scanner to, let's say, have multiple anatomical images to increase your SNR later by averaging, it just crashes the scanner. So we had this funny constraint that we had to like play along with, and that was basically like our data being acquired around 7 minutes and reconstruction taking 6 minutes, so that we can stack a couple of these imaging one next to another and without crashing the scanner. So this development is very exciting to me in perspective, because actually when I came to NIH to give a talk around 2 years ago, I was talking about, again, like 0.35 millimeter imaging, but around that time we could only cover maybe 1/3 to 1/4 of the brain with multi-echo GRE, like very, very simple multi-echo GRE stuff with low acceleration. And already there I was noticing and looking at the mesoscopic veins and try to come up with new analysis strategies to kind of analyze and quantify these veins. But now I'm really excited because in the last year, we have really covered the whole brain, very large coverage, 4 to 5 times larger than before. And we reduced the scanning times like 10 times. So we are 10 times faster. So this really becomes, I think, like a very exciting moment in time, because I mean, imagine like you can go to the scanner, you can conduct your fMRI experiment or diffusion or whatever. And at the same time, by spending 7 minutes, and maybe just to be on the safe side, you want to scan twice your anatomical data, you can spend like 14 minutes to acquire 0.35 millimeter isotropic resolution living human brain data, right? At this resolution, like for the whole brain. So now, when I talk about this data, often people are skeptical about the data quality. Like they say, oh, like, but it should be noisy, or you do some tricks like this and that. No, I don't do actually any tricks other than making the subjects very comfortable and allowing them to move in between the acquisitions. This is, I think, the most critical thing that we need to do before we like try to figure out the prospective motion correction, other stuff for the more challenging cohorts, like clinical cohort. Now I'm going to cycle through 4 runs that we acquired one after another. So this is basically half an hour of scanning. And if you look at subject 7, you can see that this subject has a very big head motion in between run 3 and run 4. See, like it is a very large head motion. And I say it because I get this question all the time, like, oh, but then the subject moved a lot, everything is a mess, you cannot look at the 0.35 millimeter data, it doesn't work. Well, it is not the case, because when we pre-process this data, very simply, just doing rigid body registration motion correction, like across these 4 volumes, and here I am showing you the echo average, so this is not like single echo, but echo average data. Now I'm going to cycle through 4 different runs, zooming into pieces of the cortex in our 5 subjects. And hopefully this image and cycling through the runs convinces you that once you make the subjects really comfortable so that they don't move within the run, but they can move in between the runs, and you pre-process the data correctly, you can actually get really sharp, like very fine details of the cortex. Look at these little sticks that are going inside the cortex. I hope all of you can see it. They are a constant, and we can capture it again and again in 4 different runs, right? So it is working. These little details are not artifact or anything. They are real biological detail that are the mesoscopic veins or mesoveins. To convince ourselves even further, actually, we acquired 3 different ways, these mesoveins, using the multi-echo GRE. This is like very old school GRE data. We just acquired different slabs and stitched them together to get the whole brain view. And we had the multi-echo version of it that is around like 7 minutes acquisition time, let's say. And we had a single echo version of our imaging as well that is actually way faster. This is like 3.5 minutes, I think, to acquire the data, but it gives you a single echo. So comparing all these images, first, you can see that these mesoveins are always there. Look, for instance, here, by chance, I'm cutting like the middle of the cortex in a sagittal cut. and you can see this star shape, like 5 dots, consistently appearing. These are really the meso veins that are diving inside the cortex, and we acquired it in 3 different acquisition protocols. So there is, to me, no doubt that these features exist, and you can really measure them without worrying too much about head motion. Like you can really do it, right? And this is just as the last step to convince, hopefully, all of you that when we do a bit of minimum intensity projection, I think along like 3 millimeters in Z direction, you can see that these intracortical meso vein details are visible in all the different types of acquisitions. By looking at it, we choose the multi-echo API because I don't show the other data, but I am convinced that multi-echo API has the best like distortion characteristics and SNR characteristics to get the meso veins out of your image, even with using single run, a 7-minute good run. So, okay, now I would like to talk about a part that I am even more passionate about, just compared to just acquiring the data, because like acquiring nice images is good and you get a good feeling. It looks like a brain, you see all these details, but extracting meaningful information out of them is, I think, the main challenge. Because at 0.35 millimeter isotropic whole brain data, like there are not too many quantification methods and analysis like pipelines established that tells us how to like deal with this data, right? There are a lot of details. Like look at the white matter. I'm not even going to talk about the white matter, but you see a lot of like details there. So how can we study this data and extract information out of it? For that part, actually, funny, like one day I was reading the Duvernoy's book from 1999 about vessels. This is one of his like last works, I believe, before he passed away. And there, in the chapter where he talks about the cortical vasculature, he says anyone who needs to study the cortical vasculature first need to recognize that there are 3 main classes of vasculature. First one is called leptomeningeal, second one the pial, and the third one intracortical. So I was already intrigued here because I was like, what the hell does it mean, leptomeningeal veins? Like I never saw this keyword, right? Whereas Duvernoy was there, like telling it in his chapter a couple of decades ago. So it turns out that leptomeningeal area is a very important area because it is like, there's a little like schematic I redraw based on the textbooks. So there's the dura mater, you have the big sinuses inside there, and there is the leptomeningeal area that consists of arachnoid, pia mater, and subarachnoid space. And this space is actually rather important because if you can extract the hemispheres, and this is what Duvernoy was doing to generate those nice images back in the day, he was basically removing the dura mater, but not touching the leptomeningeal section of the brain to create these nice visualizations. So by taking our cue from Duvernoy's like surgical methods to extract the brain and highlight the vessels, I basically tweaked the usual brain extraction and segmentation algorithms a bit to get the following segmentation. So I have first the leptomeninges tissue that is basically following Duvernoy, that doesn't include the dura mater, but everything below it inside. Then I segmented the white matter and the gray matter as usual. And the right side is there just to tell you that this is done for the whole hemisphere, not just a slice. So now, just by using the leptomeningeal segmentation that is done correctly, here I am rendering a 3D volume that is just the like a reciprocal of the T2 star weighted data. So what you are seeing here is essentially T2 star weighted MRI data. Like there is no segmentation in it other than creating that coarse leptomeninges mask. And just by using that together with the modern volume rendering methods, you can have access to this. I mean, like maybe the movie is not playing so smoothly here for you. I'm not sure. But basically, you can see all the details of the leptomeningeal veins. And this is already interesting and important for me because then we compared this to Duvernoy's method that was taking like hours to like inject all the vessels, then prepare them correctly. Then there had to be a professional graphic design artist that was taking the pictures, rendering them by hand, to create these textbook images. And now maybe we are not there 100% compared to the pile details, but to a very large extent, now I can do something very close to Duvernoy using MRI with data acquired in 7 minutes, right? To me, that's like the exciting part of it. of course, just looking at some other renderings of Duvernoy from his textbook, you can judge how close we get to the leptomeningeal vein visualizations. And more, you can see it in our preprint. I will not spend too much time looking at the details here. But there is one interesting observation I made, because now we can rapidly create these leptomeningeal vein images, right, for any like living human, basically, that we put at the 70. Then I started looking at across subjects, and I noticed that there are some very large variations between leptomeningeal patterns. For instance, look here, subject 1. Between the left and right hemisphere, in the right hemisphere, there's this big loop, basically, that is formed, but that is not the case on the left hemisphere. However, when I look at the subject 10, it has similar loop, but now on the other hemisphere and not on the right hemisphere. So this already makes me question that, well, what type of like biases and patterns do these type of leptomeningeal vein variations account for in fMRI data, right? Because when eventually like the deoxygenated blood difference is detectable to some degree in the leptomeningeal veins as well. So now I'm just questioning like how much of the maybe intra-individual variation is kind of captured by knowing where the leptomeningeal veins are. This is just a question for the future. Then we, of course, like this was a very much zoomed out view of our meso vein data. Now we had to build up new methods and visualization tools to kind of zoom in. And here you can see that I am zooming in to the Heschel's gyrus that is kind of tucked inside a kind of rather big sulcus on the lateral side of the brain. And by using some like segmentation and data rendering methods, I can cut out that part, surgically remove it, and I can render the veins that are lying on top of it. And by the way, I can also color the arteries separately than the veins, because when you have the whole brain vascular data, and arteries also do appear, at least the large arteries, you can follow them anatomically and figure out whether they are really arteries or veins. So based on that information, you can even separate to some degree like big arteries and big veins, and you can see the small veins. Arteries are often like invisible in this resolution. Okay, so this is a bit like establishing a path for the future, because this type of visualizations I would like to use to quality control the pile vein segmentation methods. There are already some papers that are claiming and establishing like vascular segmentation and various filters, maybe deep learning based methods. But the crucial part, in my view, for judging the performance of those algorithms is actually like having a good enough visualization way so that we can quality control the outputs. And so far, I didn't encounter any like algorithm that satisfied me, to be honest, like to give like a good enough vein segmentation. That's why we spend time on making the visualization the most convenient so that it is set for the future quality control steps. So now that's on the side. I am coming to the, like every section is, I'm basically more excited. I'm coming to the like even more excited part of it. That's the intracortical angiography architecture. I really like this because intracortical architecture is really hard to deal with, and I really like it because the intracortical angiography architecture has different space filling properties, depend on which kind of angle that you look at it or which scale that you look at it. What I mean is the following. For instance, when you look at the pile surface, you see the vessels there as like rivers, basically connecting to each other and so forth. But if you pile away some layers of the cortex and look at the, let's say, the middle gray matter surface, you will end up seeing these dotted pattern peppered around. That is basically the big ones are the veins, and the small dots that you are seeing that actually show a lack of capillaries around them is the arteries that are diving in and out of the cortex. When you look at it from the side, and these are all pictures from Duvernoy's work, you can see that actually the veins have like cone-shaped drainage basins. So it immediately like makes me think that, oh, like what if I have a neuronal activity here versus there? Like how this cone-shaped draining will kind of distort and affect my laminar activity results. And on top, when we zoom out a little bit, we can see that there are even capillary density changes across layers and across areas. And there's like a bit like hidden, but some literature on it actually from 40s that shows areal differences between capillary densities. Okay, so now I am going to show you one aspect of these intracortical veins, that is the radial aspect I call, and in a way that I'm pretty sure you never seen before. So here, what you are seeing here is a mid-gray matter surface. That is basically like a surface that cuts the cortex from the middle of the white matter to outer gray matter boundary. And here I am simply sampling the T2 star weighted value. So if it is dark in T2 star weighted imaging. If it is bright, it's bright in T2 star weighted imaging. And you can already see that there is this peculiar dotted pattern around, right? So what happens when we inflate this? So when we inflate this cortex and look at it, you can see that this pattern that is peppered around these dots are basically all over the cortex. And these are basically the meso veins that I was talking about, like these veins that are ascending from the cortex in a radial fashion relative to the white matter surface. We are basically now at 0.35 millimeter capturing like all of them, right, at the mesoscopic resolution. I mean, at least to like I wouldn't say like all of them, but the ones that are, as Duvernoy labels, as class 4 and class 5 for sure, because these are the ones that kind of span the deep layers to the superficial layers. Actually, class 1 even continues to the white matter. When I looked more in detail in these maps and actually created different layers of the cortex, such as the superficial, middle, and deep layers here, I noticed that some of these dots are really continuing from the superficial to the deep part, following basically class 4 or 5 veins, intracortical veins as classified by Duvernoy. But some of them, they actually stop in the middle. So, which means that I think it is safe to say that at 0.35 millimeter isotropic resolution, using the multi-echo, multi-shot 3D EPI method, we can see down to class 3 intracortical veins in living humans, right? And this is to me like I don't know if this will be such an important detail of the brain, but just I am excited by this fact. You know, you put a living human inside, after 7 minutes, you can see the details of the cortex to this degree. Okay, so once I saw these veins, I started thinking about how can we start quantifying these veins? One way is the following. So we have the inflated cortex. So I can do a bit of signal detection, basically, like I can detect those dots, these dark spots as red areas, and then I can create a, it's called a Voronoi diagram on the mesh, which basically assigns the nearest vertices to the vertex as labeled here. So it basically creates like a cell around these mesoveins. So once this type of computation is established, now you can compute the surface area that falls within each of these cells. And this I call the drainage basin area. So going back to Duvernoy, like imagine like this, you know, now imagine that you cut this from the middle. Basically what I am claiming that we are measuring the drainage area here as we see from a mid-gray matter surface, like this size. But of course we are in 3D, a bit more advanced than Duvernoy. And nicely, using some other methods, like we can convert these detected mesoveins into a completely new brain map. I am not aware of anyone else computing anything similar to this. Like if I am really incorrect, let me know. But like basically we can count the number of mesoveins per centimeter square, like passing a circular kernel around the surface and then really like quantifying the number of mesoveins that fall. And interestingly, and I would like to be cautious here though, this is just one hemisphere I'm going to show you. There are some areal differences. Like for instance, if you look at this longitudinal sulcus, you can see that one part of it is way more densely occupied with mesoveins than the other bank. Or you can have a look at maybe the Hesh's gyrus region, the medial part of it, you can see the increased amount of mesoveins. Maybe if you really look around, you can see some other areas. And here, just because whenever I show it, people ask about the sagittal view, I show you the sagittal view. You can already see that the visual cortex shows really high amount of mesovein density, and maybe some areas there. So I'm just excited that this map is computed. It seems to show some regional variation, right? And I'm like, my future question is that, okay, first, whether these patterns are consistent across individuals. and hopefully these are not byproducts of the specific like algorithms that I'm using here to calculate these things. And if they are consistent across individuals, how do they affect our fMRI signal? Having more mesoveins or more densely populated mesoveins in one area versus the other, or maybe how does it explain the resting state signal and so forth? Okay, so at this point, I would like to switch to more interactive part of my talk. And I would like to share with you a piece of software that I've been developing. Okay, you see.
Faruk,
yes.
If people have questions about the slides, should we wait for later, or should we?
Maybe I can answer at the end. Would it be fine?
Sounds good. Sure.
I cannot see chat at all. So okay,
don't worry, chat is quiet.
While I was dealing with all this data, one constant trouble is that this is a lot of data, like 0.35 millimeter whole brain, multi-echo, right? A lot of echoes and so forth. And I really needed like a new viewer that is fast enough for me. Like other viewers were not just fast enough. And now I will like sidetrack a bit, but at the end, hopefully they will converge and you will see the point. So here I loaded our LayNii test data. And you can already see that maybe a bit choppy over Microsoft Teams, but on the right-hand side, lower side, you can see that I can very quickly look at the time courses. This is nothing so new. Other softwares can do it. But then I got inspired by fMRI's Instacore and made a completely independent implementation of it to basically create the correlation map. So where I can move my cursor around, and in real time, it computes the correlation between that voxel's time course with any other voxel that you see. So this is pretty fast. However, you might say that, oh, this is very little data. It's just 3 slices, nothing much. That's why now I would like to show the strength of this implementation in 0.8 millimeter whole brain data that actually Renzo nicely shared. This is the Kensho dataset. Some of you are aware of it, I know. Now let's enable the correlations and just have a look around. And by the way, like I reprocess this data and it is basically just motion corrected. There is nothing else in it. No high pass, low pass filtering or anything like that. However, look, when I was browsing this data, I saw, oh, here we go. This is the auditory network, like very easily visible there using the real-time correlations. And I can have a look at the visual cortex and see the visual activity similarly. So I'm sure that some of you did those explorations in using fMRI Instacore. However, when I was looking at it, I noticed the following detail. So look here. There is this basically snake around that is quite strongly negatively correlated with the visual cortex activity. Right? And luckily, like many years ago when Renzo was acquiring the Kensho dataset, I was planning to acquire the same subject for my own high-res anatomy, so 0.35 millimeter anatomical data. And when I see that snake, I recognize that this is actually an artery that I am used to seeing it in this subject. And here I'm going to show you the GRE data, that is whole brain that we acquired. And see, like this is the snake that I was showing. It's negatively correlated. And now I'm going to move across the time. So these are 6 echoes from 3 milliseconds to 21 milliseconds spanning range. And I would like you to notice something strange here. And that is this white halo that is around the dark tube. So this dark halo is actually something I talked about 2 years ago when I was in NIH. And this is the blood motion artifact. So when the blood is moving so fast inside your arteries and large arteries, when you are when the time difference between the phase encoding and the readout stages are increasing, you end up seeing, particularly at GRE data, where you have very like short readout times, this white arterial signal going out of the artery itself. And this made me think for a second, because when I look at my EPI data, 3D EPI data that is 0.35 millimeter, I do not see this artifact. So now I am cycling through different echoes here. So the artifact is not visible. Oops, I lost it. And then I was thinking, okay, why is it happening? The reason is the following. When you have a long readout duration, such as the case with the fMRI data, and in this case, longer readout time, 3D EPI anatomical data, this artifact basically gets smeared out of the image through the case-space sampling and image reconstruction, so you do not really see clear trace of it, as you would see in a GRE data, like in here. And that made the connection with regards to the Kensho dataset, this blue snake, because when an area is active, like the big arteries dilate, they vasodilate to bring more oxygenated blood there. But when they dilate, and if you are doing EPI sampling that has a very long EPI readout time, you are basically getting affected by the blood motion artifact, which means that the artery itself looks just a dark hole in the image, and it doesn't have like a bright signal in it after you do your EPI sampling. And that's why when the arteries dilate, they basically create an opposite effect in your fMRI signal. They create, so when there's activity, the arteries dilate and their signal is not inside them due to the blood motion artifact. Therefore, they just go down together with the activity. And finally, like thinking about that and thinking back on the LayNii test data, I have noticed the following. So we have the task activity modeled here very simply, but there are these like little blue dots around, you see? So one of these dots is definitely a vein because it looks dark. So this is a vein in a T2 star weighted data. This is just the bold data. I'm not showing you the vaso data. And like this part is negatively correlated with the task activity. Actually, you can see on the lower right-hand side that when I hover over this voxel, the white signal goes like anti-phase to the orange signal or the green signal. But there's the other guy here that is also negative, and it is a very strong negative correlation with the activity. It's like minus 0.75, the correlation value, right? And however, when I look at a different normalization of it, that basically doesn't like normalize the both time courses together, you see that the white time course is way higher than the gray matter activity. That's the orange time course, which means that like this is not just a vein there. Like there is something else going on, and I suspect that there's actually an artery inside there, and when there's activity and there's enough blood motion artifact in it, so when there's activity, it dilates a bit, and it creates this negatively correlated activity in there. I hope I make some sense. And we can discuss in the following minutes. Okay, so this was like a half LayNii IDA demonstration for you, and half like some just to see like how I'm approaching this. So like starting from the mesoveins anatomy, try to combine things there, but then luckily we had the same subject with the fMRI, with the Kensho dataset, so we could align everything and look at it in detail. And all of a sudden there we noticed some details that are maybe hard to explain. And now it brings me to the last part that I wanted to show, because together with Renzo, we were looking at this quite a bit, also Alessandra. This is the Frisco data from Renzo that is at 0.4 millimeter isotropic. So this is the data that Renzo sent me, pre-processed by him. And there's like 300 million voxels in it. Yes, and so now if I enable a simple model, let's have a look there. This is just ones and zeros model to see like some activity. So what do you see in this 0.4 millimeter fMRI data? Like red is basically a correlation, like, and I do not normalize it in some weird way. It is if it is red, it is 1. If it is blue, it is -1. So look, first of all, of course, the pile veins are all showing very high correlation with the task. Why? Because as I was talking about at the beginning of my talk, based on Bob Turner's 2002 paper, this is where the like oxygenated blood like accumulate in the veins, and they give the highest oxygenated to deoxygenated blood change together with the task. And that's why we are just like seeing the pile veins popping up at this data. But there are also other details. For instance, look here. This is a leptomeningeal vein. This is like rather large, you can see. It's a large dark thing. And one side of it is kind of positively correlated with the task. And there is like another side in here that is negatively correlated. So I actually don't know exactly what's going on in here. And if any of you know, maybe we can discuss soon. And look here, there is this negatively correlated arm, which I suspect is actually an artery based on what I explained like 5 minutes ago. So this is an artery. There is enough blood motion artifact in it so that it looks like just a dark hole. It is vasodilating together with the activity, and it creates, when there's activity, this increase of the dark values through partial voluming. So just to say that like all this cycle of looking at the anatomy at 0.35 millimeter, thinking of the 0.8 millimeter data, coming back to then the exciting 0.4 millimeter Frisco data, I think we have some, or at least for me, exciting avenues to explore and think about with regards to how we can maybe first be aware of these different like signal activities, and two, can we leverage them? You know, like maybe you can say, oh, if it's like a negatively correlated with my task, I just get rid of those voxels. But why? There's information there. Like there's good information, right? We can maybe leverage that information. And the other side is that these pile veins are popping up quite a bit when you are really at a lower resolution. So what does it mean for layer fMRI? Should we just block out like the pile veins and then just focus on inside the gray matter? Also, like what does it say about the 0.8 millimeter layer fMRI? Because at 0.8 millimeter, as you might think, like there is more partial voluming, right, with the superficial layers of the cortex. So maybe this increase that we were seeing from deep to superficial layers of the cortex in an ROI level was just a byproduct of the partial voluming of the pile veins contributing to the superficial layers of the cortex. And we were just not seeing it at 0.8 millimeter, right? And this is why we need to go to 0.4 millimeter data and have a careful look at these fine vascular details. Okay, now I will go back to my talk. Oh, by the way, also in LayNii, we can do things like this. This is a flattened piece of motor cortex, and you can see all the meso veins there, and we can overlay them with the activity. This is a 0.8 millimeter activity. I will not talk too much about it, but just to say that like all these things will be coming more and more in LayNii IDA in the future. It will be like a one software to do all these flattening and layer analysis and activity maps and so forth. Let me find my presentation. Okay, I talk about these things. So just my final takeaways. Our multi-shot, multi-echo 3D EPI protocol is ready to be used. So if any one of you wants to see like how the brain looks under 7 minutes with T2 star weighted imaging, it's like really there. It has excellent contrast, whole brain coverage. It's to me like ready to be used. And no like extra pre-process or post-processing is needed with regards to like image reconstruction. And follow LayNii and LayNii IDA news on the also on my YouTube channel, because I will be talking about, as I put more features in LayNii IDA, I will be talking about that first. And just some practical takeaways, like actually like I process all these anatomical images at 0.175 millimeter isotropic resolution, which presents its own challenge. Like there are many reasons why I do it, but I think this is the best like a nominal resolution to look at these meso veins data acquired at 0.35 millimeter. And when you are around this limit, you need often computers that are like more than 30 gigabytes of RAM. I'm just saying it because if you plan to acquire this data, maybe also think about what type of hardware you have and what do you need to like work with it. Also, the last thing, these meshes that I was showing you with the meso vein density maps and so forth, they are like really large. They are reconstructed on the 0.175 millimeter nominal isotropic data. So each mesh has like 4.5 million vertices. This is like almost like 30 times larger than a standard, let's say like free surfer or brain voyager mesh, right? So it's like when you load one of them, you are loading like a 30 subjects at the same time. So when you are computing things on these surfaces, you need to pay attention to like algorithms and which computational limits that you will encounter there with regards to scalability. And with that, I would like to thank my collaborators, particularly Rudy for giving us the sequence development help, Desmond for setting up the protocol at Maastricht and preparing it for us to use, Alessandra at the beginning to help us fine-tune the 3D EPI parameters. I think she's like one of the best experts actually right now in 3D EPI like optimization. And Dimo, of course, for countless scanning hours that we spent together. And my other collaborations that are Saskia, Sebastian, Mario, Renzo, Kendrick K, and of course, my boss, Rainer Goebel. Thank to you all. And that's it.
Awesome. Maybe before we jump right to the questions, I would want to second the last thing, like by meaning it's available to be used for NIH folks. This means that the sequences and protocols are like literally on the scanner. You just need to drag it and like append it to your protocols that you have. And by the LayNii IDA viewer that you developed, it means that you can download it from GitHub. And I did it. And so I want to. There's no installation required, right? It's a self-contained thing. You just download the binary and you execute it, and that's it. So it's by readily available. It means really like 5 seconds away. Yeah. Okay. Are there questions? I see
Nadia.
Nadia.
Hi, Faruk. Thank you so much. What a wonderful talk. I wanted to ask, how do you think that your technique would affect our ability to quantify activation that's happening deep within the brain, like in the thalamus, where there are large draining veins, like intracerebral veins with perforation into those areas? How would this help?
Yeah, funny that you bring it out, because I kind of hold myself from going into white matter and the thalamus, but there are already a couple of people in Maastricht that came to me asking exactly the same question, because they were suspecting that some of the activity or like activity differences that they were observing across subjects, they were thinking, oh, maybe there's like a big vein passing by in one subject but not in the other. Can we get at it? And I think it is plausible to think in this way, and I think this T2 star weighted acquisition that we have shown here is the way to go to also look at the thalamus. I mean, I look at the thalamus as well. It's just that I don't have a task specific to engage in the areas there yet. But yeah, it's like it's to be done.
Well, I do have a task, so we can always talk about that later. I do have a task. Yep.
I see Burak.
Yeah, nice talk, Faruk. This unilateral differences in leptomeningeal veins is quite interesting. I mean, it might be just angiographic differences, but it might be also related the physiological ongoing during the scan, like, sleep state or attention. Are you considering doing like runs with different tasks to see that how these veins are dilated? On like 7-minute run in average, that may highlight a very interesting functional differences.
Yeah, actually, I have more than enough data to write about, so I am not planning to get any more data at least like for a year or so. Dimo can vouch for it. And so if you want to do something like that, Burak, just go ahead. I don't have the bandwidth to do it, honestly. But it makes sense to me, yeah. I mean, I don't know how much veins dilate. We were discussing this with Renzo, like, do they dilate? If it's like, how much and so forth. Yeah, this is the direction to go, I think. Yeah.
To my knowledge, they are like blood reserve in the brain and dilates 50-60%. I mean, they increase a lot of size. They also play a role in intracranial pressure and all the also pumping CSF too.
I see. Oh, cool. Yeah. I mean, I didn't know that detail, but yeah, good to know. Now we can measure them.
Perfect.
We see. Okay, Peter is also unmuted, I think. Yeah.
Oh, well. Okay, I'll just quickly. Yeah, great talk. That was really creative, nice work. So I have two things. Well, three maybe. So one is that when you make those nice maps of the the ascending vein sort of territory, some could argue, at least in the idea of cortical surfaces, that that's like the upper resolution and the upper functional resolution, and they would be like, oh, okay, so we get all this resolution, and now we have to go back down to this is what the upper resolution is. And then but then also another thing with the veins, or the veins or arteries with the dark areas. I mean, one way of testing that potentially would be modulating the flow compensation. You could actually modulate your gradient such that, you know, it accounts for velocity changes potentially. So because I think actually it could be just a velocity shift. I mean, you say, right, it shifts it, but it also could be like I don't know exactly maybe if you use crushers or not, whether it's a flow void that occurs, like if it flows, gets excited and it flows outside the plane, and then when you're imaging, but if it's just GRE, it probably wouldn't happen in that regard. But then at the end of the day, so you have this, yeah, I would definitely pursue the Instacore a little bit more to see, you know, what correlates with what in terms of the details. But then at the end of the day, so people might argue, okay, so all right, you have this, you can see it. Maybe you can mask out the veins, like you said. But then what do you do with it? I mean, how do you really use it to calibrate? And that's a hard question in that regard. But no, those are just my.
Yeah, thanks. So I noted them. So this upper resolution part, I actually left some slides out, but indeed, like I actually computed an average distance between these meso veins for the whole hemisphere in one subject, and it comes out to 1.4 millimeter in like distance, like between any like meso vein. So of course, one can think that, or maybe on the brain surface, our like resolution limit, right, is just 1.4 millimeter diameter, like circles, kind of. Well, it sounds like that at the beginning, but I think when you think of the details, it is not like that, because Duvernon shows that there are big veins that dive to the deep part of the cortex, and on the superficial parts of the cortex, there are shorter but more dense veins and arteries that are coupling. So when I think of that, I think that if we have enough resolution to really separate the pile veins out and just look at within the gray matter, actually, like, and if we think that the sparsity of the diving veins are dictating our resolution limit, actually, like in the deeper layers of the cortex, we might have lower resolution, but at the superficial layers of the cortex, in a hypothetical scenario, we actually have more resolution. So there's like a varying resolution inside that, if our resolution is really coupled with the veins, which might not be, maybe, depending on where the like control mechanism is with regards to the. But yeah, this is something definitely to watch out for. This, like, what does it mean for the like this tangential brain surface maps resolution limit? The other one was flow compensation. I think you were talking about the arteries, this like bright signal going out of the arteries. So we couldn't do flow compensation because we were looking at many echoes, so 6 echoes there. And as far as according to my knowledge, you cannot really compensate in a meaningful way more than like 1 or 2 echoes maximum. So that's why we get to that. And also, like, I think flow compensation, you need to tweak it for a specific like a velocity range for arteries, as far as I understand. But when you do like a whole brain, it's like all type of ranges, right? So maybe it's better just not to do it, and then understand the effect on your image. The other one was what to do with the Instacore. So first is, I think, being aware of the like weird, strange, unexplained behavior that is in your data. I think that's definitely one way, because I mean, who knows, you know, maybe like just thinking about that weird one voxel, someone will come up with like a new understanding of the physiological neurophysiological coupling. Other thing is doing quality control. There I agree with Paul Taylor a lot. Like this Instacore is like really needed to do quality control and see like your data is fine to begin with. But 3, like I think when you do like a connectivity analysis in general, and this is I'm a bit naive with this connectivity field, but like people boil down areas into like ROIs, right? Like just parcellate the brain into 200 ROIs, and there you go, do some connectivity. But there, like if you have this like big like snake that is passing by in your area, that is exactly like antiphase to your activity there, you will be like just canceling out your signal, right? If you just like put together all the voxels there. So like you will be killing some. So basically, like areas near big arteries run a risk of showing like a bad connectivity fingerprint because you are not looking at this counter phase like arterial behavior that is going on there. But if you are aware of it, maybe then you can like sign flip that activity and then still use it, you know, for your connectivity maps and so forth. That would be my first answer to say like what to do once you see that Instacore based like anti-correlated patterns.
I mean, or you could, I mean, it might give up some signal. I mean, you're thinking of using it, but also you could do, I love Instacore as far as that's concerned, but using Instacore and then having a tool that can readily either regress or orthogonalize
Oh, yes.
the signal. So
actually, I didn't want to say it, but I am working on implementing a regress out right now. So it will be like a real-time regress out once you catch the nice signal. And I will just remove it from the rest of the voxels and just have a look, you know, catch the artifact from the eyeball, remove it out from the rest of the image. Like I think like there are people who are a bit cautious about this. I am aware of it, like regressing out too many things, but I'm gonna do it. So let's see. I see some hands.
Right,
Divya,
so
I see.
in order, it's wait, Sruku, please.
Shukran.
Yeah.
Hello.
Yeah.
Thank you, Faruk, for your amazing talk. I really enjoyed those measures on the, you know, veins and the distance and the, you know, mapping of those surface space, which actually I believe has many consequences for applying in aging and dementia kind of research, because you can also look at the distance between those and the number, like how in aging it's changing, because you also pointed out that individual differences in the vascular structures, and who knows, maybe aging, some of these pathways are clogging or just reduced. My question is, since you're using multi-echo and you showed us intensity contrast in like kind of this blood flow related sharp drop because the read time was kind of like a diffusion, right? It just goes away. These perivascular spaces, which are really important for CSF movement and the water flow in and out of the brain to clean up the waste products like lymphatic system. So I wonder, some of these brightness changes has, or could you use your method or combine it some with other methods, with diffusion kind of methods? I will send you in the
Sure.
in the chat. There's a paper just published, and can you really use it to dissociate the CSF possible CSF motion?
I would say maybe, I don't know, but we did discuss this with Dimo actually as a potential future avenue to explore this white matter vasculature and perivascular spaces and so forth. There I kind of got stuck a bit because I looked at the literature a little bit. It seems that people are using like T2 imaging there, whereas we do T2 star imaging. I don't know why they only do T2, but I am like rather naive about it. So I would, like, if you send some pointers to me, maybe I would enjoy like looking a bit more and thinking how this can be
Yes, I
explored.
got very excited by your talk, really. Like, it's very beautiful, amazing work. You did everything. It is so good. And I follow up with it in the chat. I
Sure.
put a link. It may represent fully what I'm talking about, but I will be very happy to talk to you later again. Thanks.
Thank you.
So next we have Divya.
Hi, Faruk. Really nice
Hello.
talk. Yeah, I have a bunch of questions. So the first thing is in some of my vessel scale data, I see that the flow displacement artifacts in arteries kind of vanish in smaller arteries. So it really feels to me like if we can go to higher resolution, I don't see that movement. Larger arteries, yes, I see the kind of blurring and very clear difference when I go to multi-echo GRE. Do you have any insight into?
Yes.
if that
So
makes
the-
sense to you.
Yeah, it makes total sense. I agree with you completely, because this artifact like behaves as a function of the velocity. Like, so when you go to smaller arteries, like just because the bifurcations, the velocity, blood velocity inside like slows down, right?
Mhm.
And therefore you get less and less displacement. So when you are at this really like small arteries, like it's actually a bit strange, because in the big arteries, like blood motion artifact occurs and they look like black holes basically in the image. And if they dilate, it's like a signal drop, right, through partial voluming. But if you are at a small artery, because there is no blood motion and there is like oxygenated blood in it, then you see, due to CBV, like a signal increase. So like that's I think the critical part, like how big is the artery, how big is the velocity inside, and that kind of dictates what type of CBV signal you will be seeing. If you detect any, it can be like going up signal or going down, depending on the blood motion artifact.
Yeah, that's interesting, because then my next question to you is, when you generated those vein surface maps, I was blown away, because I have such a tough time getting cross-section of these vessels and, functional data, right? Like, because we are just acquiring like a slice or slab. Do you see arteries? Like, it seems to me like they should just have different T2 star, and you should see like white dots along with your black dots there. Do you see them? Or...
So this was a long time discussion. I always like insisting to call them vessels, because I was saying that I'm not 100% sure all everything I see is a vein, right? But now and again, and thinking about it and discussing with other people, I noticed that like, okay, like veins decrease, like they have a very fast T2 star decay, right? Especially at 70. But the arteries, when the blood motion artifact is not there, they have like a good strong signal in it. So they look like just gray matter. That's why I converged on saying that, okay, everything, or like vast majority of what I'm seeing as these dots on the surface, dark dots, are just veins. That's why I start calling it mesoveins.
I see.
Actually, like,
so I
together
wonder,
with
I wonder
Saskia,
if you go to a higher flip angle, get rid of tissue, maybe you'll see white dots and black dots.
Maybe something like this is suggested to me by Nick Weisskopf a couple of weeks ago, like using higher flip angles. I even tried it in the scanner, but I'm not so hopeful that like something interesting will be pulled out so easily. But that's just me, right? Like, if you want to try, go ahead.
Okay, yeah. I know I have 2 more questions. Do we have time, or is it
Sure.
okay?
Yeah,
Okay.
people, please feel free to drop out if you need
Tyler
to.
was,
Yeah, because I saw Morgan also had Andrew.
Yeah.
She also had a question.
Maybe she had to leave.
No, you're good. You're good.
Okay, yeah.
You go ahead.
Yeah, so my next question was more to do with artifacts. Like, we see so much B0 and 3D PI. How do you deal with B0 distortion correction in your data, or do you even do any?
So
is it?
So you are talking about the geometric distortions, right, in the lower part of the brain. So actually, this is why we are using multi-echo. I don't have the images in this laptop, but we have this single echo version of it that's like long readout time versus multi-echo. Like, one benefit of multi-echo 3D EPI is that because your readout is like shorter content, and like the geometric distortion is not as extreme as you see in a like fMRI style long readout 3D EPI acquisition. You really see it, and that's why we choose the 3-echo multi-echo, because there we are almost, I mean, I wouldn't say like we are distortion free, but compared to a single echo version of it, where the front part of the brain becomes like a horn, we are pretty well off. Like, there is no hornness there. So that's why I recommend
and also
multi-echo
I'm
3D
sure your resolution also helps, right? Like, distortions automatically kind of are reduced.
Yeah, that's right. There's another
right?
like part of it, like the single echo version of this 3D EPI has the mesoveins more blurred, like across different subjects. I looked at 5 different subjects, and this is also, again, the same thing. This susceptibility differences and this geometric distortion is even like visible at the level of the mesoveins. When you do multi-echo that has like less geometric distortion, you see the mesoveins even sharper.
Okay, great.
In my view, in 5 subjects.
Yeah, and my last question was related to that large vein that you showed which was negative in the center and like positive around. You know what I'm referring to, right? So we've been seeing similar center surround effects in arteries, and I think that's my colleague Sebastian Prou's work at ISMRM. And we were kind of thinking that it's more to do with vasodilation in arteries, like to do with like what we're seeing surrounding the arteries could be related to the diameter changes, and that kind of is opposite of the flow changes or velocity changes that we're seeing. I wonder if there's a similar explanation with veins, or do you think, because it was like surrounding,
Yeah,
right?
it
Like
is
it
strange.
was very nicely just a halo on the.
Yeah. Also, like we see other examples of it with Renzo in other data at 0.4 millimeter and stuff. But like I'm not exactly sure what is the explanation. I even think that maybe somehow there's like some fluid dynamics going on there, like the oxygenated blood is like pouring into the big vein that is like passing by, right? Like a highway, right? And it like somehow, I'm a bit like speculating, but it somehow creates like a turbulence there, and you get this like weird like mixture of things, and you get like a counterphase behavior at a part of the vein. But I mean, I don't know. But one thing is for sure, I am seeing it in data consistently, even at lower resolution 0.8 millimeter data. When I look back using Instacore in these big veins, big leptomeningeal veins, I see this like strange, one side of it is positively active, the other side is negative. Like, so I'm a bit thinking like, as well, like what's going on.
Yeah, so those are two effects. So we also see that in a lot of our arteries, actually, where we see like negative on one and positive on the other. And we think the vessel is moving, and that's why we are seeing that.
Could be.
But the one effect that I'm referring to in your data, it's not one side positive and one side negative. It feels like intravascular negative, boundary positive, like that I feel like might be a dilation effect. I don't know. It's something to just think more about. I'm not very sure.
I mean,
about
this
it,
might be
but
related to the perivascular CSF and water content is higher. So I don't know that it's changing because blood has water too, but oxygenated blood. So you guys know better than I do probably, but water content in the perivascular space, it is also flowing, it's moving too, but not as fast as blood. And actually, the good thing to test this is very easy, like adrenergic system, like kind of anything arousal kind of thing. If you have the subject very rested state, like sleepy state or something, and then dilation is happening, and then when you wake him up or just get the attention demanding task, neuroadrenergic system is LC is just sending signals and all the constriction happens. In that case, perivascular space opens up, and then you see the blood, the ventricles, and they're kind of constricting, and there is the opening in the CSF space, and then when it dilates back, it pushes the CSF further. So, I mean, it can be really tested, and this is a beautiful method. And I think Burak does like arousal things too. Now you have subject like sleepy state, like deprive the subject and do this one maybe 10-15 minutes, and then once in a while poke the subject with some auditory noise or something.
Okay, interesting. Yeah.
Can I add something to what Sukru was saying? Actually, perivascular spaces should have a very different T2 star than your blood. I feel like if you have multi-echo data, and if you suspect that is a perivascular space, you will get a hugely different T2 star there compared to your venous blood. Venous blood should be a very less T2 star, and perivascular space should be like 100 or 200, milliseconds. So you might even be able to test it in your current data if you just fit your T2 star, right? I think that might also be a possibility, right?
Well, there's gradients outside the vessels that cause dephasing, though, that the perivascular space experiences. So, it's not that maybe, the CSF in itself doesn't, but if it's experiencing the gradients around the vessels, that affects the T2 star. So
So it might not be that clear.
Yeah.
But Faruk, you have multiple echo times, right? This dephasing is, you're showing the time course only one echo time, right? It may change in different echo times.
Time course, you mean the multi-echo
Yeah,
data?
the time course, yeah.
Yeah, I was showing, I don't know which one you refer to, but often I showed just the echo average. But yeah, I have like in the 3D EPI, I have the echo time like 10 millisecond, 24 and 39 millisecond. In the GRE, I have from 3 millisecond to 21 millisecond, like 6 echo times, much more dense.
Yeah, that
I
may
mean,
matter if it's emotion or if it's just the deoxygenation around it.
Yeah, one thing that could be interesting is that looking across echoes, those vessels might change. It might show an interesting signature, as you know, the oxidation effect would cause things to go in and out of phase, or maybe some aspect of the velocity. I mean, it could have an interesting echo time dependence. That's not just exponential. It could be oscillatory.
In the anatomical images across echo times, I see the blooming, like between 10 millisecond to 24 to 39. They just get like distort the space around them more and more. You really see it, the big veins.
Okay. All right.
Eric, I was wondering,
Yes.
so the correlations in your new viewer are really working really cool, but obviously a lot of the stuff that we're looking at, because it's in the temporal domain, sometimes anti-correlation, like what you're talking about, and phase differences can be kind of misconstrued. They can be two sides of the same coin. Do you, given that you've put a lot of effort into making things really fast, do you plan to put in like lagged correlation maps as well? I feel like that would be really helpful.
Yeah, totally. Actually, it was already there, then I took it out in the last moment because of some instability. But this is exactly the direction I'm going for. Also, like I would like to actually implement along these lines.
The onset? Sorry, you have the time course controls onset versus offset. Is that what that's going to control?
Yes, there will be onset, offset, and there will be a shift. There used to be. I just took it out, so you can like move it around. Many people requested this actually. Like they were looking at the sinus, for instance, picking up the signature from the big sinus, and they wanted to shift it and see its correlation with the other parts of the brain.
Very cool. That'll be really helpful for a lot of problems.
I hope so.
All right, we are quite a bit over time. So if there are no other burning questions, then maybe we can continue discussing it offline. All right, thanks a lot, Faruk. This is awesome, and I will send the link around.
Sure. Thank you.
Thank you.
Bye-bye.
Thanks, Faruk.